It's not that hard to build some RAG or chatbot application that works 80% of the time, but building something that's actually robust and working in production is very hard. In this video, I want to tell you about some of the most common failure modes that I've seen across hundreds of deployments in production, and try to give you some indications on how to solve them. So one of the biggest failure mode of RAG when you're building your retrieval pipeline is not integrating keyword search as part of your hybrid search system. I still hear many engineers basically only using dense embeddings when they're building their search pipeline and not integrating keyword search with a reciprocal rank fusion algorithm. I think that's a big mistake because there are many questions where you actually need an exact match between the query and the document. A very simple example is if you're looking for a SKU or very specific product ID, you need to have that kind of matching, and embeddings, especially dense embeddings, are pretty bad at that. So not incorporating keyword search in your pipeline is a big mistake. After keyword search and hybrid search is completed, you can use a reciprocal rank fusion algorithm to merge the results from those two search pipelines. And this will maximize your result and give you really good accuracy without hurting your end-to-end latency. So that's a very simple thing that you can implement today in order to boost your accuracy results. The second thing that I hear a lot is people not using a re-ranker model. What is a re-ranker model? A re-ranker model is a model that's going to take your initial first pass search results. So maybe you're going to take your top 100 or top 200 results and re-rank them based on relevance. You might wonder why you would need a model like that if you already have embeddings that give you a score between 0 and 1. The problem with embeddings is that they're trying to encode a lot of information contained in one sometimes pretty large chunk of text, into only a certain number of dimensions. And it's very hard to encode that information independently from the query and still be able to match the query with the exact document all the time. Maybe the intuition is easier in one dimension. So this is the intuition in one dimension. If you have 4 vectors of text, v1 to v4, and you want to index those and put them in a one-dimension line, the closest thing that you can do is put v1 next to v2, next to v3, next to v4, based on what the documents contain. So if you're trying to retrieve information with a top k is equal to 2, you will be able to retrieve the blue and the yellow one because they're next to each other. So if you're asking about apples, you will be able to extract the information from the blue and the yellow. Similarly, you can ask about rabbits, and with the top k is equal to 2, you'll be able to retrieve the red and the green ball. However, with the top k is equal to 2, there is no dimension where you will be able to retrieve the blue and the red one only, because they're not next to each other. The same thing happens in very large dimensions. Because of the way your embeddings are storing information, depending on the query and the top k, you might not be able to retrieve the information that you need, but also more importantly, you will be able to find the cluster where all of your relevant documents live, but that doesn't mean that you're going to be able to retrieve them in the right order. So here, if I increase my top k and I have top k is equal to 3, I will be able to retrieve the blue, the yellow, and the red one, but they're not going to be ordered properly. The blue and the red are not going to be in the top 2 position. So this is exactly why you need a re-ranker model that can take the results from this initial first pass search and then reorder them based on relevance. This is extremely important to basically push the most relevant results up and boost your overall accuracy. So not using a re-ranker is probably hurting your accuracy quite a lot. So there are many benchmarks that can show you how much better your retrieval pipeline could look like if you added a re-ranker model. So here, compared to the OpenAI text embedding models, you can see that the ZeroEntropy re-rankers, for example, are bringing a huge improvement, and it's just in one API call. So not having a re-ranker is something you could fix today with just a few lines of code, but that would give a very nice bump to your overall accuracy. The third most common mistake that I see in retrieval pipelines is not setting a proper threshold in the relevance of the documents. What I mean by that is that I see many pipelines basically setting a top case equal to 10 or 20. But the problem is, depending on the question, you might only have 3 relevant results. And for other questions, you might have 50 relevant results. And in order to give the best generated answer, you kind of want to have the flexibility depending on the actual scores and relevant scores that your pipeline is giving you. So you want to be able to play with those relevant scores that your pipeline is giving you so that you can either give only the top 3 results if that's all you need, or way more results if that's also what the question requires. That allows you to give a more diverse answer, a more targeted one, also depending on the question. And you're never feeding garbage to your LLM. The problem with most re-rankers is that the way that they assign scores is not very consistent. So in this graph, what you can see is basically how the ground truth relevance scores correlates to the scores that different re-rankers give to a document given a question. So what you would want ideally is a linear correlation between the ground truth and what your re-ranker is actually outputting. The problem is for most re-rankers out there, that's not the case. For Voyage and Cohere, it's either an inverse sigmoid or a sigmoid that's the closest fit. And you can see that there's a very wide margin of the score setting. Voyage's re-ranker always gives scores between around 0.5. If you want to set a threshold to 0.7 and only take the documents that are above this threshold, that will be very hard to do for this re-ranker because the scores are always between around 0.5 and it's really hard to give any kind of meaning to the absolute score. It's the exact same problem for Cohere's re-ranker. At ZeroEntropy, we tried our best to solve this very big problem. We had to do a lot of calibration, but the result is that now the scores of the re-ranker correlate linearly with the ground truth, meaning that if zerank 2 outputs a score of 0.7, it actually means 0.7 relevance across all queries, across all verticals, and all languages. So you can actually trust this absolute value of the score, and you can set a threshold confidently, knowing that you'll broadly get only documents that are higher than 0.7. And this is also going to give a pretty nice bump into your accuracy, but also the quality of the answer that your LLM is going to generate based on the documents that you provided. So you might wonder, well then I'll just use an LLM and prompt it to give me calibrated scores. Using LLMs as re-rankers is actually a pretty terrible idea, depending on how you do it. I'll explain more about that towards the end of the video, so make sure you stick around for that. By the way, if you're curious about zerank 2, you can check out all of the benchmarks that we ran on this model in our blog, and the link is in the description. Another super common mistake that I see in retrieval pipelines is not putting enough effort on the data itself that you're indexing. It's a very common saying, but garbage in, garbage out. And without proper handling of the data itself that you're going to be indexing and embedding, you're very likely to get poor results. And by that, I mean multiple things. First, the quality of the parsing that you're choosing if you have PDF documents is very important, but that's not it. You should also pay a lot of attention in the way that you're chunking and contextualizing your chunks. Your chunks should roughly have the same size, because what we notice is that very long chunks might get picked up a bit more than very short ones. So you should try to pay attention to the size of the chunks that you're picking, which should always be roughly the same. But you also need to contextualize your chunks, either by hierarchical summaries, but also by adding tags and metadata, so that at query time, you can also filter by this metadata, which is going to reduce the search space quite significantly and automatically boost your recall also quite a lot. So the way that you want to contextualize your chunks might depend on your exact use case, but I would spend a lot of time there thinking about the different tags that you could use, maybe even generating tags for each chunk, making sure that you're recording where the chunk is coming from, generating summaries at different levels of granularity, and adding that to contextualize each chunk at the embedding time. All of those things are things that you should definitely do to improve the overall recall that you're going to get. So lastly, I still hear many developers using LLMs as re-rankers. This is not a great idea for multiple reasons. First of all, LLMs have not been fine-tuned on this re-ranking task. So even if you prompted them very carefully, explaining that, oh, if the document contains X, Y, and Z, it should be a 0.5 relevance, and if it only has X, it should only be 0.2, they're still going to hallucinate. And even for the smartest model, there is a significant percentage of time where the response is going to be 3 million or something completely random, or it's going to want to add an explanation even if you didn't ask for it. So it's pretty difficult to work with those models for something like a structured output like this, where you only want a calibration between two numbers. So you can try to constrain them, but it's not going to work fully. And if you try to fine tune them, well, this is exactly what a re-ranker does. So it's much better to use a re-ranker, which is a much smaller model, a much faster one, and a much cheaper one, and one that was specifically fine-tuned or trained for this task of outputting a relevance score. Even if you really didn't want to compare against using an LLM, we have actually run these benchmarks, which you can see here. So using an LLM as a point-wise re-ranker is definitely not a great idea. We have seen some people using LLMs as list-wise re-ranker, meaning that they would give multiple results inside the body of the LLM and ask it to reorder them based on relevance. This is great if you only have very few results, but it doesn't scale and it doesn't work in production because you're randomly going to have to wait 30 seconds if you have more than 5 or 10 results. So it's really not practical in prod. And we have even compared against using Gemini as a list-wise re-ranker. And zerank 2, for example, still wins against Gemini. By the way, if you're curious about how we're building hybrid search at ZeroEntropy, you can check out our architecture, which is in our documentation at docs.zeroentropy.dev. And the link is also in the description. So here are some of the most common failure modes that I keep seeing over and over again. There are many more, and we'll keep doing videos to try to explore all of them and try to find solutions for them. For now, if you're curious about context engineering in general, you can watch the webinar that we hosted with other companies like Mastra and Mem0 at the link right here.